Now if you take compressive stress can be written as resisting force by divided by area, cross sectional area. It is called cross sectional area A. Then what is the resisting force? Resisting force is equal to the applied force P under equilibrium. So that's why this is called as a push force P divided by area A, equal to P by A. See, always remember the stress is nothing but ratio of resisting force by cross sectional area, not the applied force. The definition itself, it is a resisting force by cross sectional area, and it is at a point. At a point, stress you are calculating at a point, okay, at a particular plane, on particular plane, okay. So when the object is under equilibrium, this resisting force will be equal to the push force P. That's why this R is equal to P, okay. It is not P by A, but R by A is the general formula, but at under equilibrium R will become P, okay. Both are same. So this is a compressive stress. So similarly, compressive strain can be written as change in length by decrease in length divided by original length. So this is called as the dl by L. So this is how you can calculate the compressive stress, okay. So this is the definition of compressive stress. So next will be shear stress. So let's go into the shear stress topic. Third kind of stress is shear stress, okay. It means when stress induced in a body when subjected to two equal and opposite forces which are acting tangential across the resisting tension. For example, I will write down definition first. Stress induced in a body when subjected to two equal and opposite forces which are acting tangentially across the resisting section. So as a result, the body tends to shear off across the section. The body tends to shear off across the section. So it is known as a shear stress. So the strain induced in this phenomenon is called as shear strain. So I'll explain you with an example here. Let us take a riveted plate, okay. These are the two plates which are riveted, okay. Riveted in the sense two plates are joined with a rivet. Rivet is some kind of nut or bolt, okay. Even you can see in the railway platforms where the bottom the floor, okay, of overbridge or rivets, okay, you can observe in practical scenario where these rivets kind of joints applied to join any two kind of plates, because these are the two plates. So it is generally I can say, so these are the two plates which is attached like this, okay. There is a rivet, they will put a hole here, through hole, and they will just punch one rivet, and out of the top they will keep one kind of they will weld. So it is like riveting, punching they will do, and they will they will do a riveting operation so that these two will be joined together. So here, when you are applying a force this direction P and this direction P, now what happens if you observe at this cross section? At this cross section, if you observe, so because of the application of forces, okay, here if you see, when you apply two equal and opposite forces which are acting tangential across the resisting section, so these two forces are acting tangential across the resisting section. It is acting tangentially in the sense in this direction. Okay, so because this portion is pulling in this direction, this portion is pulling in this direction. Okay, but what happens to the rivet? The middle rivet will be subjected to some kind of tangentially, right, at this resisting section. So as a result, what happens? This rivet will get failed. So it will happen like this. So it will happen like this. This portion will come like this, and this portion will come like this. This is the rivet. So like this. Okay. So rivet will fail here. Okay. It will fail like this. So this kind of failure, or this kind of application of force is called as a shear stress. The stress induced because of this kind of tangential force is called as a shear stress. Okay. No, I told you in the previous just before, some 10 minutes before, about shear strain, right? Shear stress is nothing but the shear stress produced due to strain produced due to shear stress is called as shear strain. Shear stress is nothing but the stress which is acting parallel to the cross section. So now this is what, here the shear stress will act parallel to the cross section. Okay, that is called as a shear stress. Now, how you calculate the shear stress? We'll see. So I'll take that same cross section. Let us take that rivet. Okay, I'm taking some portion of that rivet. So consider this rectangular block. This rectangular block. Okay, now I have applied a force, P force, parallel to this rectangular block. Okay, let us say height of the rectangular box is small h and length is L. Okay, and this is the AB. I'm just mentioning the corner points of the rectangular block. Now, if the bottom is fixed, AB is fixed, now I applied a tangential force here. Because of the application of force, now I apply like this. Okay, for example, this is the notebook. I have applied like this force, and bottom is fixed. Okay, now if you draw the free body diagram, let's take a cross sectional area here, x. If you draw the free body diagram of the top portion, this is the free body diagram. Okay, now you take x, d, c. Now this is applied force P. Now if this body is under equilibrium, it means that there will be some resisting force, right? So resisting force will act at this cross section, but the direction of resisting force will be in this direction, R. This is the resistance. This is the resistance, right? Okay, so it means that I'm taking example. This is a book. Okay, now in this book, bottom is fixed. This is fixed. I fixed it. Now I applied some force. When bottom is fixed, I am applying some kind of tangential force like this. It will be having some kind of deformation. Okay, but the internal cohesive force between the molecules will try to oppose this force, right? So within the elastic limit, what happens? It will deform. Okay, and if you take some portion of this, okay, so here at this cross section, let us say, so there will be a opposite force which will act at the intersection. So this is the applied force and this is the opposite force which will act at the intersection. So that resistance force here. So similarly, if you take the bottom section, so this is the resistance force which will act in this direction, because this side is this direction, this side is this direction, in order to keep this under equilibrium. Okay, now according to definition, shear stress can be written as it is represented with a tau. Okay, shear stress is nothing but tau, normal stress is nothing but sigma. It is written as shear resistance divided by shear area. So it is R by A. That is how you can take. Then what is R? R is nothing but, it is applied force. R is P, and A is nothing but cross sectional area. Whatever the cross sectional area you have at XX cross section, it is called as a cross section area. You will mention this denominator, that area. Yeah. Now shear stress will act in tangential direction to the area over which it acts. It is always tangential. Okay, it is not normal. It is the tangential stress which will act, and because of this shear stress there will be a shear strain, right? Then we'll see how to calculate shear strain. So let's take how to calculate shear strain. So let us say this is the same block I have taken. Okay, I have applied force. Because of that, it is having a deformation. The red one is deformation. Okay, now initial is A, B, C, D. So final is C dash, D dash, and let us say this is H, and this is DL. This is DL, and this is H. Okay, and this is the shear strain phi, dependent on the shear strain. So shear strain is nothing but, I told you, right, it is the angle. It is the angle between the this line, original line, and the deformed line. Okay, it is called shear strain. Okay, and this angle you have to find out how much is this angle. You have to find out. So now you see the triangle. From triangle ADD dash, shear strain phi can be represented as transverse displacement divided by distance AD, isn't it? Because it is nothing but triangle. From this triangle I can write down, if it is sine phi is nothing but opposite side by hypotenuse, right? So here opposite side will be DL. So what is the hypotenuse? Hypotenuse is nothing but this one. Red line should be AD dash should be hypotenuse, but see, this is very, very small. Now the length AD dash or AD both are same. Okay, that's why it is written as distance AD instead of AD dash, because it is very, very small angle. For small angles we can, this length and this length can be taken as equal. So instead of taking this AD dash, I am just taking AD. So this is nothing but D dash by AD. It is nothing but DL by, or I can write down this is DL, what I mentioned, DL by H. This is phi. So this is how you can calculate the shear strain. So shear strain is the change in angle. Okay, change in angle between the original line and the deformed line because of the shear force. Because of the shear force you apply. Okay, so this is how you can calculate the shear strain. So I'll stop it here, and whatever the topics I have discussed in this lecture is from the book called R.K. Bansal, Stempometers by R.K. Bansal, and I have shared this book in your Google Classroom. You please go through the what are the topics we have discussed in this Google Classroom, and the next topic will be elasticity and Hooke's law. I will discuss in the next class. Thank you.